Hello, so today I'm going to walk you through my code for the M4 Final Hackathon. In cell 0, I install the required packages like open pyxl and then balance learn, and then I import all the necessary libraries including NumPy, pandas, matplotlib, scikit-learn models like GBM and TensorFlow, and I also set a fixed random seed for reproducibility, and this ensures that my result remain consistent every time I run the notebook. So here in cell 1, I loaded the training and test datasets from the Excel files. According to the output, the original training set has 110,000 rows and 22 columns, and a test set has 11,744 rows and 22 columns. I displayed the first few rows to confirm the structure, and I see that the target variable's diabetes binary is present only in the training set, and the test set contains an ID column that I will later use for submission. And in cell 2, I performed the basic EDA checks. So I print the column names and check for missing values. From the output, I see that both train and test datasets have 0 missing values, which simplifies preprocessing. And however, I find 7,287 duplicate rows in the training dataset. And that is a significant number. And I remove those duplicates, and the training set size drops from 110,000 to 02,713 roles. And this step is important because duplicate roles could bias the model and inflate performance artificially. And in cell 3 here, I examined the class imbalance. So from the output, I see that the class 0 has 87,629 samples, and class 1 has 15,084 samples. And that means approximately 85.3% of the data belongs to class 0, and only 14.7% belongs to class 1. And this confirms strong class imbalance, and that immediately tells me that accuracy alone will not be meaningful. If I predict class 0 most of the time, I could achieve over 85% accuracy without detecting many true diabetes cases. And this is why F1 score and ROC become more important metrics. In cell 4, I compute the correlation matrix among all features. I visualize it using a heat map. So from the matrix, I observed that no pair of variables shows extremely high correlation, and that means multicollinearity is not severe, and I can safely keep all features without removing any at this stage. And in cell 5, I split this clean data set into training and validation sets using stratified sampling. From the output, I see that the training size is 82,170 rows, and the validation size is 20,543 rows. And I also define the reusable valuation functions to compute the accuracy, precision, recall, F1, and RLC, as well as a threshold search function. And this prepares the framework for consistent model comparison later. And in cell 6, I trained a logistic regression model here to with the different regularization strengths using various C values. From the output table, I see this all versions gives very similar results. The F1 score is around 0.443 across different C values, and accuracy is about 0.72, precision around 0.313, and recall around 0.5757. So this tells me that the logistic regression struggles with this data set. Even though recall is relatively high, the precision is low, which pulls down the F1 score. So in cell 7, I tuned the classification threshold for the best logistic regression model. And the output shows that the best threshold is 0.6. And after applying this threshold, the F1 score increases to about 0.453. And compared to 0.443 before tuning, accuracy increases to about 0.778, precision improves to 0.355, and recall becomes about 0.625. So this demonstrates that the threshold tuning alone can improve the F1 significantly without changing the model. And in cell 8, I apply the PCA to retain the 95 percent of the variance and then retrain the logistic regression. However, the output shows that the F1 score drops slightly to around 0.448. This means PCA does not help in this data set since there are only 21 features and no strong multicollinearity. Dimensionality reduction does not improve performance. And in cell 9, I trained a strong light GBM model. So I calculate the scale pulse weight based on class imbalance. From the output, I see there are roughly 12,067 positives and about 70,103 negatives in each fold. And that confirms the imbalance ratio. And during the five-fold cross-validation, I observed the validation binary log loss for each fold, and early stopping kicks in at around iteration 11 for each fold. And most importantly, I performed the threshold tuning, so the best F1 score achieved is approximately 0.46, which was with the best threshold around 0.278. This already outperforms the logistic regression and PCE models. And in cell 10, I applied the SMOTE to oversample the minority class. The output shows that the SMOTE and the log regression achieves F1 around 0.404 and the ROC arc around 0.758. And the SMOTE plus the regression achieves F1 around 0.419 and the ROC of around 0.777. So these are weaker than the tuned light GBM model. So although SMOTE satisfies the class imbalance handling requirement, it does not improve the performance in this dataset. And in cell 11, I compute the asymmetric error cost. So using a cost of 1 for false positive and 5 for false negatives, the example cost for the tuned random forest confusion matrix is 9,000.922. And this illustrates that missing positive diabetes cases is more costly than false alarms, and that further justifies why I prioritize recall and F1 instead of accuracy. And in cell 12, I implemented a neural network with the 2 hidden layers and drop out for regularization. So here in the output, the best threshold for the neural network is 0.25. And the F1 score reaches approximately 0.465, which is the highest among threshold-based models, and accuracy is around 0.807, precision about 0.329, and I recall about 0.572, and ROC arc about 0.819. So this confirms that nonlinear models perform better than linear ones on this dataset. And in cell 13, I combined all results into one comparison table. So from the output, the neural net tuned threshold ranks first in F1 around 0.465, and light GBM is close behind around 0.46. Logistic regression tuned threshold is around 0.453, and SMOTE models rank lower. And this summary clearly shows that the threshold tuning improves the performance and advanced models outperform baselines. And in this final cell, I performed the full five-fold stratified cross-validation with the light GBM and average test probabilities across the folds. And from the fold output, the values are kind of similar and they're consistently above 0.8, indicating strong and stable ranking performance. And instead of predicting the probabilities across instead of like predicting the binary labels, I average the predicted probabilities across folds. And this is critical because the ROC AUC evaluates ranking quality across all thresholds. And finally, I just generated the submission CSV. So I think this final light GBM CV model is the strongest and most competition-aligned approach, combining imbalance handling, cross-validation, early stopping, and probability averaging to maximize the RLCOG. So yeah, that's the end of my presentation, and thank you for listening.